Okay, thanks for the introduction, Ellie. It's great to be here again. This is my second trip to Israel in a year, which is really always exciting. So I actually have the next two sessions with you. And my goal is really going to be to explain how smart contracts, what they are, if you've never heard of smart contracts, and specifically, hopefully enough about how the Ethereum platform works. We'll get into details that even if you've never dealt with Ethereum before, if you've sort of only thought about cryptocurrencies through Bitcoin or maybe Zcash or whatever, that you'll sort of understand what the platform gives you, what you can do, and that will set up some of the rest of the talks today about applications of smart contracts and things that people are trying to do. So I guess the same way Ellie asked how many people have tried to explain blockchains maybe to somebody else, how many people have tried to explain what Ethereum was or what smart contracts were? Oh, OK, so this looks like at least half the room has thought of this before. So again, I'm going to sort of start from the beginning. So some of this, maybe if you've seen before, you can work on your knitting in the back. But hopefully I'll get into some new stuff for everybody. OK, so as I said, I'll be giving you the basic overview, and then Vitalik will be taking over after me, and he'll talk more about some security issues of what's challenging about using smart contracts, talking about future proof of stake. He'll also be giving you more hands-on demo. So I'll be talking a little bit more about sort of where Ethereum came from, a little bit of historical perspective, as well as sort of how to understand it conceptually within computer science. So some links to computer science ideas that existed long before Ethereum. OK. So on the road to Ethereum, I guess you could have a historical debate about when really was the people have been thinking about contracts certainly for a long time. Usually, Nick Szabo gets credit for really exploring this idea of smart contracts. For the most part, Nick was writing about this online in the 1990s when very, very few people were thinking about it. I think most people at the time actually sort of had no idea what Nick was talking about. It was very abstract at the time. There were some ideas that sounded really exciting, but this was kind of a long way off. So this was before Bitcoin, before blockchains, before there had ever been any kind of successful cryptocurrency. Nick Szabo was writing at a very conceptual level, saying, basically, what if we could replace these really difficult to understand and predict contracts in the legal world with computer code? At a core level, that's sort of similar to what Ellie was talking about earlier. Can we sort of replace something that's been a societal function, specifically courts and judges, and understanding what some language means, what some contract means? Could we replace this with an algorithm? So very, very much the same thing. And again, I think it's pretty impressive that Nick was writing this at the time, because we hadn't really had a successful demo of this. Bitcoin was still 15 years away at this point. So before we had this sort of, now a lot of people are thinking, how can we replace slow, trusted, old-fashioned processes with code? But this, I think, is pretty cool, came about long before that. And so again, you could think about if there's such a thing as a smart contract, then it's always nice to call your invention a smart something, because then whatever the old way of doing it becomes the dumb version. But basically, a dumb contract is a traditional concept. You write down in English, whatever language you're working in, what is supposed to happen. Both people sign a piece of paper. And then we have this kind of societal expectation that this now becomes some rules with some legal backing behind it. Of course, at the time you do this, it's really just a piece of paper. And you have to, again, bring in sort of the trusted legal system to make it enforcing. I'm not sure if anyone's ever actually written a legal contract to reveal the preimage of a hash, but this is a very, very simple example of something that you can do easily with smart contracts, even in Bitcoin, actually. Even before Ethereum, you could do this. But just as an example, you could write this contract. And in fact, if you wrote it and signed it, it would be a legal contract. OK, so I guess calling them traditional contracts instead of dumb contracts. This is sort of what we're trying to replace to make them smart. So again, instead of writing them in natural language or even some, usually contracts are not really written in natural language in the sense that, you can be a fluent speaker of English or Hebrew, but if you didn't go to law school and spend a lot of time understanding exactly what words mean in a legal context, you probably won't be able to interpret a traditional contract exactly correctly. But in any case, we'll sort of replace whatever language is being used with code. For assent, for the notion that two parties agree to a contract instead of them signing a piece of paper, we'll use digital signatures, of course. And then the important part, of course, is that we're replacing judges or other, maybe private arbitration, whatever, with this decentralized platform. Ethereum is one example that will interpret the code and decide what's supposed to happen. In terms of the actual enforcement, I think this is another real difference. In the traditional world, if people don't actually follow the rules of some contract, if they don't do what they're supposed to, you can fine them, both money or you can, it's not common, but you can do other types of fine or compelled action, in a traditional legal system. For smart contracts, really the only thing you can do to punish people is make them pay. And in fact, you can only really compel them to pay money that they've already put on deposit. So a little bit more limited there to basically enforce that everybody does what they're supposed to. It almost always takes the form of people put in a deposit, and if they don't do what they're supposed to, then they lose their deposit. So unfortunately, there's no, well, maybe fortunately, depending on your viewpoint, there's no Ethereum jail. So the worst you can lose is money. OK, so before getting to Ethereum, just wanted to point out that this idea was on the radar of Satoshi Nakamoto, who did put scripting language into Bitcoin. Actually, I think a lot of people learn about Bitcoin and don't learn that there are scripts involved. I was actually curious, so how many people were sort of aware that Bitcoin actually uses this scripting language to express things? OK, so most people. But I've certainly seen, you can understand Bitcoin, and I think you can use Bitcoin perfectly well with a simpler model where the only thing you can really express in Bitcoin script is that this specific key has to sign for money to move. And that's sort of the way it's almost always used in practice, so it's a perfectly valid understanding. But of course, under the hood, that's sort of expressed with this scripting language. And really, in a transaction output and a transaction input, there's two halves of a script. They get put together and run, and that's how you decide whether or not Bitcoins can move. So, if you've never looked at Bitcoin script, it's not super interesting. It's very unusual for computer code in that it's this very, very confined language without things like loops that we're used to. But it does give Bitcoin scripts a nice, well, what was perceived as kind of an essential property at the time, which is that interpreting them, you only scan from left to right. Again, this thing can't loop, so you just execute all the instructions in the script one after the other. You push and pop things from this stem, maybe. But notice that the instruction pointer basically only moves from left to right. So you're very, very limited in what you can do in a Bitcoin script. But the benefit of that limitation is that these things can't run forever. Their execution time is limited to how long the script is. So that's just an animation. If you've never seen Bitcoin in the stack, but basically you scan the script from left to right, you mess around with the stack, and then hopefully if someone's going to actually get to spend money, you push, you return this results of true. That's all you can really do. The details of this aren't super important, except to realize that it's this intentionally very, very weak scripting language that was built into Bitcoin. So as I said, it's sort of there's no looping by design. And the goal there is just that the time it takes to run and the amount of memory or resources the script can consume is very, very easy. You just look at how big the script is, and that's kind of an upper limit on how much work it can do. Right, and it's not Turing complete. There's sort of a philosophical argument about whether Ethereum or any other system is really Turing complete. That's maybe not worth spending a lot of time on, but Bitcoin scripting language is definitely not Turing complete. And Turing completeness, I guess if you're not, if you have never heard the term before, the simplest way to explain it is it's basically the most general class of computer that we know. So your phone is Turing complete, your laptop is Turing complete. It's basically as expressive of a computer as we know how to build. So we can draw like a very strict algorithmic separation saying that Bitcoin is much weaker than most other things in the world that we think of as being computers. OK, so I spent all this time telling you that Bitcoin script is kind of weak. So what can it actually do on the positive side? There are some specific things that it is pretty good for. So expressing some access control restrictions in terms of multiple keys. If you want to say 3 out of 5 keys have to sign to move these Bitcoin, or even express a tree, like 2 of these 3 or 3 of these 5 are enough to move the funds. That's actually very natural to express in Bitcoin script, and probably one of the main things that people have actually used it for in practice, which is pretty useful if you're running a business and you want to sort of have access to funds controlled by some quorum of people rather than just having a single key control everything. And then there are some kind of fancier applications that people have spent a lot of time thinking about. You can swap Bitcoin for Ether or Bitcoin for currency on another chain. You can sort of have different people put in randomness for a lottery and force them to reveal what randomness you're contributing. For the most part, even though all of these work and have been done in proof of concept, are not really being used in practice very much. And then the big one at the bottom there is doing payment channels, things like Lightning Network or other ways to do it. There's a lot of excitement that this may be a big opportunity for scaling Bitcoin. But again, not really being done on a large scale today, but it's something that you can do with Bitcoin script. As far as I know, though, this is pretty close to it in terms of applications of Bitcoin script, which is sort of not what we'd want. Conceptually, obviously, you'd want the system to be so powerful that it's not sort of a finite set of things that you can do with it. And of course, that's the kind of thinking that led people wanting to create a more powerful system. OK, so really before Ethereum came about, sorry, yeah?
Can you explain why Bitcoin is a very volatile currency? Like, is there a reason for it?
Volatile in terms of the exchange rate?
I mean, as a currency, it's volatile, yeah.
Yeah.
So I wanted to know if there's a reason in terms of the way it was built that caused this to function this way.
Oh, boy, that's a long philosophical question, probably. No, I don't think there's anything about the technical design that makes the price fluctuate. I think it's a new asset, and people aren't really sure how to price it. So that's probably the shortest answer I could give you. We can talk more, I think, offline if you like. But I guess I'm maybe not an expert on asset pricing, so I probably can't give you a much more complicated answer than that. Right. OK. So back to the story here. So Bitcoin script really gave developers a taste of the fact that you could sort of do things besides just payment with a cryptocurrency. And like I said, it's a relatively small number of things. So within a few years after Bitcoin launched and started gaining traction, people started proposing, writing forum posts saying, I wish we could do X with Bitcoin. I wish we could make the scripting language a little bit more powerful so that my sort of pet application could be supported. And I can say I was guilty of this line of thinking. So FutureCoin was actually a paper I wrote with some colleagues at Princeton where we said, prediction markets are a really cool thing from economics. It would be great if we had decentralized prediction markets. And we only have to add 4 instructions to the Bitcoin scripting language, and then we can build prediction markets. The problem, of course, you can hopefully see already is that when a whole bunch of different people are saying, well, we just need to add a few instructions, and then we can do the cool thing that I think is really important, that's not really sustainable. At a certain point, you have to think about making the platform more general rather than extending it a little bit for every feature that people have. But this was a phase that we went through, and I'll walk you through how that worked with Namecoin. So Namecoin was actually the first fork of Bitcoin. It was the first project that said, we like Bitcoin, but we want to make it a little bit better, so we're going to fork it and make an altcoin. And the goal of the Namecoin project was to support a decentralized naming system. So instead of relying on DNS with name servers and the root zone and all of this international politics around who gets to decide who has which name or where which IP address which name resolves to, we're going to do it in a decentralized way. And again, this is the temptation, is to say, oh, it's so easy. We just need to add 3 instructions to the Bitcoin scripting language, and then we can build DNS. So this looks really, really deceptively kind of simple and exciting. So this is how Namecoin works. 3 instructions are added. And then anybody can sort of claim a new name. So for example, if I wanted to register my domain name, this would be .bit. So there's actually some browser extensions so that you can browse to .bit domains, which are driven off of Namecoin. Not being used by a whole lot of people, but you can do it. It all got built out. It's kind of interesting to see. But anyway, if I wanted to claim jbonneau.bit, I just have to sort of post 3 different, really just 2 different Bitcoin transactions. So I first kind of claim the name. So with this name new instruction, I say, I'm getting ready to claim this new name in the system. I'm going to commit to the name. So I post a hash of the name with some random value. And the point of that is that then nobody can tell which name I'm about to register and try and steal it from me. So without that commitment, anybody could look at the blockchain and say, oh, there's a pending transaction. Someone's trying to claim jbonneau.bit. Why don't I front run that and get in before them and steal the name? So doing this kind of 2-phase commitment prevents people from doing that. So anyway, that's why registering a name takes 2 instructions in Namecoin. But basically, I commit to the name and say I'm getting ready to claim it. And then once that is included in a transaction in the Namecoin blockchain, then I post another transaction, and I run this name first update opcode. And that says, OK, here's the name I was claiming. And to start with, we'll have it resolved to this IP address. And then later on, as many times as you want, you can update this name. So you can either change the mapping. You could change the owner. So you could sell your name to somebody else. But all of the updates to this name will be tracked in the Namecoin blockchain. And what's interesting here is that this was a fork of Bitcoin. So all of the old Bitcoin opcodes still worked. And you basically would post transactions that look like Bitcoin transactions, right? They still had a script sig and all that, but you just added these opcodes as well. OK. So, like I said, it's kind of deceptive to say you're just adding a few opcodes, because it's not just opcodes you're adding this big, in the case of Namecoin, you're adding this big amount of state that everybody tracking the Namecoin blockchain now has to keep track of. So in particular, every miner now, right, everybody running a full node in the Namecoin network has to maintain this big map from all the names that have been registered to what they resolve to, what address, plus whoever owns that name. Right, so potentially for all of DNS, this is this giant table that now every miner has to keep track of with potentially millions and millions of names. I'm not sure Namecoin ever got to the millions of names being registered, but it certainly got into the tens or hundreds of thousands. Maybe it's in the low millions now. And of course, for every one of these transactions now in Namecoin, you don't just have to keep track of the UTXOs and the Bitcoin state, but this additional state of who owns what name. And you have to check and verify all of this. So you've added a lot of state to the system. And in addition to adding new state, Namecoin also adds new fees to the system. So in particular, in addition to sort of the fees that you pay in Bitcoin to get your transactions posted, there are kind of fixed fees in Namecoin for all of these name-specific operations. So when you register a new name, when you transfer a name, you pay some fee in Namecoin to make all that happen. And of course, the reason for these fees is that you want to make people pay for the fact that they're editing this global state that all of the miners have to actually track. And the way Namecoin chose to do it was to basically just fix costs of these different things. Arguably, they didn't get these costs quite right. Namecoin had real problems with squatting throughout its whole existence. So with Namecoin specifically, a lot of people went in and registered a whole bunch of names. People said, hey, I'll take Google.bit and Microsoft.bit and Technion.bit and anything that people thought might one day be interesting. And the fees here weren't quite enough to discourage that. So that was sort of a tricky bit about Namecoin. They had to pick all these fees to try to incentivize behavior. And maybe they didn't get it quite right. OK, so if we compare Namecoin to FutureCoin, which was, like I said, the one I worked on that was dealing with prediction markets, I'm not going to bore you with the details of how all the prediction markets get maintained in FutureCoin, which is a proposal that never got built, so it was really just a white paper. But the important thing is that it had to do the same exercise as Namecoin, basically introduce some new state. So for the prediction market system, you have this big list of open markets and who's bet on what and who's owed what. You add new opcodes, so there's new ways for people to express, I want to open some new betting market. And then you have a bunch of fees that sort of regulate how people can edit this new state. So really, any kind of new functionality people were proposing, you always had to propose these three things. Sort of what is the new state that everybody has to track? How do you express changes to that state? And what do you have to pay to change that state? And if you think about it, Bitcoin really has these three things already. They just weren't really expressed this way in the Bitcoin white paper, and this is usually not how Bitcoin is explained. But essentially, Bitcoin has a big global state. In Bitcoin, it's the set of UTXOs, unspent transaction output. So this is basically all the bits of money on the Bitcoin blockchain that are still available to be spent. The opcodes in Bitcoin are sort of just the transactions you sign to redeem them. And then there's the notion of fees. And in Bitcoin, the concept of fees is very, very loose. So it's kind of an open market. You can attach whatever fee you want to your transaction, and the miners can essentially do what they want, although, of course, there's the default policy, which is what most of them follow. And notice, I think this is the one important comment here. The fact that Bitcoin has this state, the UTXO set, was not described in the Bitcoin white paper. Often not taught, in the first half hour of learning about Bitcoin. It's sort of something you think about later when people are talking about implementations, the fact that you track these UTXOs. But it's actually, it's pretty core to Bitcoin when you think about it. OK, so now I'm going to sort of zoom out a little bit and talk about how could we make this more general. So the abstraction that dates back to the 1980s from distributed systems research, way, way before cryptocurrencies, is this idea of a replicated state machine. And the idea is basically a bunch of different computers will all track the state of some system, and there will be some consensus mechanism where they agree on what that state is, and the state can evolve over time. So the full sort of formal definition here, the important thing really is that you have some definition of what states the system can be in, and then everybody has to agree on this concept of transitioning, where given some new input to the system, you produce a new state and possibly some output. OK, so I know this is a little abstract right now. But I think that the benefit of this formalism when you look at blockchains is it's very, very easy to express what a blockchain is. As Ellie said, he didn't offer a definition of blockchain, because trying to define a blockchain is a really good way to get into an argument, I think. At least have a lot of different people say that they have a different idea. But here's one possible definition of a blockchain, hopefully not starting an argument here. But you can basically think of it as an ordered list of inputs to some replicated state machine. There's some start state. So way down at the bottom, kind of a throwaway in the definition of a replicated state machine. Yeah, we have to agree on a start state. In a blockchain, we give that start state a special name, the genesis block. But it's really just saying this is the whatever state the system starts in. But really, a blockchain just says, we started in some state, and here are all the inputs to the system that have existed. You use hashes and everything to quickly prove that it's a list that's being appended to, and you're not overwriting history, et cetera. But the payload of the blockchain is really inputs to the system. And of course, since this replicated state machine has a deterministic transition function, the start state, all the inputs in history, so everybody can compute the current state of the system today. And that's basically what happens in Bitcoin. The Bitcoin blockchain just has, each block basically has a bunch of transactions. And the miners, of course, implicitly store this set of UTXOs with each block. So note it in Bitcoin, the UTXO sets are not really expressed anywhere in the blockchain. It's just something that miners keep around in memory. And you can think of it as basically being a way of compressing this whole history of the Bitcoin system into the relevant bits that you care about right now. But you could think, and in fact, this is something people have proposed for Bitcoin and is now done in a lot of other systems, that a blockchain is actually a lot more useful if, in addition to tracking what the inputs are in each block, you also track what the current state is. So you can commit to the current state in each block. Right? So in the case of Bitcoin, there have been several different proposals that said, what if we commit in each block header to what the UTXO set is at the end of this block? And there's some really, really nice reasons to do that. Then it's very efficient to pick up the system at any point. You know exactly what state it's in, and you don't have to go back to the beginning of time and sort of replay history to understand what's going on. So I don't think that this is necessarily a requirement of being a blockchain, but committing to state explicitly certainly makes your blockchain more efficient. And there's some other benefits, too. For example, if there's ever some inconsistency, if two different miners disagree on how the transition function is supposed to work and are actually tracking a different state, you'll find out about it a lot sooner if you're committing to that state in every block, rather than just waiting to see when your difference in state will sort of cause some transaction to fail. OK. So if hopefully a little bit of that made sense. We're sort of ready to talk about Ethereum and present how Ethereum makes a replicated state machine that's in a sense universal. At least the goal is to be universal. Okay, so like I said, we want to build a programmable platform so that people won't have to keep proposing new extensions to the system every time they want new functionality. And that basically means that our transition function is going to have to include some sort of interpreter, right? So the transition function is going to have some ability to interpret programs, and the inputs to the system are going to have to be able to put arbitrary programs in. And we'll talk about how, once you have a universal system, and again, this is basically a big shared computer that we're building, you have to deal with all of the sort of classic problems that if you took an operating systems class, you've heard about, you have to regulate who can edit which state, and you have to deal with resource contention. So you have to worry now about, well, what happens if your arbitrary program has an infinite loop and tries to run forever? Or what happens if it just tries to use a whole bunch of memory? So this is sort of the attempt to represent Ethereum in one slide. I hope this is the benefit of the replicated state machine abstraction. But if not, I'll go over what this means. OK, so the state in Ethereum, the state of the whole Ethereum system at any one minute, there's a big map from all the addresses in Ethereum to what the state is for each address. So there's kind of the global state of the system, and that's really just a map from addresses to sort of the per address state. And what is the per address state? Well, every address has some code, potentially. So you can think of each line in this table, each address. It's not a perfect analogy, but sometimes it's thought of that each address is sort of like a process running in some kind of shared operating system. So each one of these addresses, or each one of these processes, if you like, has its own code, has its storage, so it has kind of its own memory space. And then the special thing that's sort of unlike traditional operating systems, every process in the system has a balance, so it has some money attached to it. Maybe the balance is 0, but it has something. And then every input to the system, some of them are sort of just a payment from A to B, but the more interesting ones are basically a function call. And we'll go over sort of gas and what all this means. But basically, inputs are a way to say, I want to start this specific process at this address. I want it to run some code. And I want to pass maybe some arguments in or pass some money in. And the gas is just a way of saying basically how much computation, sort of a limit on how much computation that process can do. OK, so the transition function, how does the state update? Basically, you take some input. You check that it's signed correctly. And then you basically just look at the address it's calling. You run some code. You pass in the data and the value and all that stuff. And you update potentially not only the state of the contract that you're calling, but as we'll see, contracts can call, or these processes can call each other. So you could potentially have sort of cascading effects all over the state of the system. So this is all sort of shoved in the Ethereum blockchain. Very, very similar to the Bitcoin blockchain. The top half here, at least, there's pointers and there's a bunch of stuff about who mined the block. But in Ethereum, there is this explicit commitment to the state in each block. So you have this big tree, which has this, represents the state of every contract. Like I said, a contract is, really the same thing as well, not all addresses are contracts, but all contracts have an address. So you have the state for each address. You have a list of transactions that are fed in. So this is very much like Bitcoin has a Merkle tree of transactions per block. Same thing in Ethereum. You have a tree of all the transactions that are being passed in. And then you have this tree of receipts in Ethereum, and this is basically the result of each one of these transactions. And it's basically just sort of some debugging output if you want, how much gas was used, that kind of thing. The interesting parts are really this commitment to the state. So again, a tree representing the entire state of the system, and a list of all the transactions that you processed in this block. OK, so you may have noticed I've been tripping over my own words a little bit with account and address and contract or process. So a little bit confusing. They all are related notions, certainly. The important distinction in Ethereum is between accounts and contracts. So at a high level, accounts are very much like addresses, say, in Bitcoin. They're represented by the hash of a public key. They have some value associated with them, some balance. And that's it. They don't have any code or storage. They're not smart contracts. They're really just for sending and receiving money. The interesting addresses in Ethereum, the sort of new thing, is that you have these contracts, and those actually have code. So they have code, and they have storage, which represents the state of that contract. And basically, the amount of money that an address has and its storage, those can change over its life, whereas its actual address never changes. And also for contracts which have code, the code never changes. So basically, once you create a contract, you give it some code. That's the code of that contract for life. And this is actually sort of usually what you want, because if you're sending money to a contract or interacting with it in some way, the whole benefit is that you want to know exactly how it's going to behave, which means you want the code to be fixed. In practice, people always ask what happens if you need to update the code for some reason. You can do that. There's sort of a way to call a library, which can be changed over time if you need to. But the base code of the contract is always going to be the same. Transactions in Ethereum can really do one of three things. You can, this type is not really explicitly stated. It's just sort of the, you interpret them in basically three different ways. You can create a new contract. So you can basically say, I want to make a new contract. Here's the code. You can do a very simple payment. Alice can pay Bob some money. And then the interesting sort of, again, Ethereum specific, where all the interesting action happens, you can actually call some contract and cause it to run some code. So all of these are sort of represented by the same data structure in Ethereum, which is just one transaction, one sort of input to the system, which is something you would sign and broadcast on the Ethereum network, and miners would include in a block. OK, so before we go to, I believe we have a coffee break, and then I'll come back and dive a lot more into the detail. What I wanted to show you is sort of a payoff of the Ethereum system, or maybe a proof that it's going in a useful direction. This is one attempt, at least. This is a very, very simple attempt. But to basically build the functionality of Namecoin into Ethereum. So remember, I talked about how Namecoin was this fork of Bitcoin. People said, we're going to make a new system specifically to build names. And then the claim I made was that Ethereum is a more general system, and the benefit is that you don't have to make a new system to do something like Namecoin. Well, this is how you would build Namecoin in Ethereum. So again, this is very simple. If you were going to build a production quality version of this, it would probably be a lot more code. There's one or two bugs in this that when I've given this, used this example before, sometimes students in the back will point out. So I know that there's a few bugs. But really, the benefit here is to say that instead of building a new system, you can add new functionality with a very short amount of code in Ethereum as a smart contract. And so really, Ethereum, it lets you build Namecoin. It lets you build something like something like future coin with prediction markets and all sorts of stuff just by writing code. You don't have to change the underlying system, which is really the benefit of moving toward universality. And instead of having 3 new opcodes, there's just sort of 3 functions you can call on this contract to say all the same functionality. I want to register a new name. I want to update it, et cetera. So I think are we going to take questions now or questions now? OK. So I'll just leave this up, and you can sort of gaze at it. And again, not production code, just an example that you can really do a lot of different stuff in Ethereum. So I think we have like a few minutes for questions, and then we'll take a break, and then I'll talk a lot more about sort of what this means and how you actually code stuff in Ethereum.
OK, let's thank the speaker, and then we'll take some questions. I'll hand the mic around, so raise your hand.